All right, it is 11 o'clock, everybody, so let's get started. Welcome to the PhD defense for Scott Leorna. My name is Todd Brinkman, and I've had the privilege of serving as Scott's advisor. Today, Scott is going to share some exciting research on a camera-based monitoring of wildlife on the large and open landscapes of northern Alaska. Before we begin, I would like to share a little bit about Scott. Scott received his Bachelor of Science in 2016 and his Master's in 2019, both from UAF. As an undergrad, Scott led and published innovative research on the effects of changing weather conditions on Dall sheep hunting and harvest. During his master's degree, he developed and demonstrated skill in the human dimensions of wildlife by exploring attitudes and communication channels among hunters, wildlife managers, and policymakers. During his time at UAF, he has been the lead author on 4 peer-reviewed publications, has 1 more in review. He's provided over a dozen presentation and guest lectures at local and international venues, and he's received half a dozen awards, scholarships, and fellowships. He has maintained this high level of productivity while raising 2 beautiful children with his wife, Jessica. And I must say, I feel so lucky to have watched Scott transition from a student into an accomplished professional and colleague. I want to stop there, but I need to say one more thing before we begin. You may not know this, but Scott was also once a famous star on the most popular reality TV show in an unnamed Southeast Asian nation. His smiling face was commonly seen on billboards and buses in major cities. So with that, Scott, I'm going to turn it over to you.
Thank you, Todd. Just to check, make sure everybody can hear me, just with maybe a nod there, Knut. Yep, all right, great. So thank you all for being here today. The talk here is going to be about an hour long or so. I'll stick around at the end to answer any questions and take comments. So I'm just going to start with a broad overview of the project and show you kind of what we're going to be talking about today. So the overarching goal of the project as a whole was to develop camera trapping methods specifically tailored to the Arctic in order to inform the utility of camera traps for monitoring wildlife in the system. And throughout these slides, there'll be slide numbers here at the top right. You can reference at the end if you have specific questions. And also at the bottom here, we'll have this status bar to see where we are in the conversation. So you can track our progress as we go along. So to start out, I'll talk about a little bit of background about the project as a whole, provide some context for the study. Then I'll move into the first chapter where we developed a method for estimating animal size or distance. Second chapter focuses on how to process camera trap images. The third chapter focuses on informing camera trap settings to collect information in open landscapes. And then finally, the fourth chapter combines insights that we had from the previous chapters in order to estimate seasonal caribou distribution and habitat use using camera traps. And then I'll end with a summary of the project as a whole and provide a few closing remarks. So to start, the Arctic is experiencing dramatic climate-related changes. So this graph here on the right, on the top is showing in red places that are warming faster than the global average. And on the bottom is showing that trend over time, with the global average being the black line and the Arctic being the red line. So what we can see is that the Arctic's warming at approximately twice that of the global average. And this is affecting a broad suite of environmental characteristics of the landscape, including changes in habitat and shrub expansion, loss of sea ice, thawing permafrost, changing fire regimes, and the list goes on. And these environmental changes can have profound impacts on wildlife populations, and including changes in habitat and distributions, and also changes in species dynamics and interactions, as well as phenological mismatches between habitat availability, forage availability, and animal movement. In addition to these environmental changes, the Arctic is also experiencing, over the last few decades, a big insurgence of industrial development. So you don't need to be able to read the text here, but this is a map of current oil and gas development on the North Slope of Alaska. The point here is just to show that there's quite a bit of activity going on in northern Alaska. And this industrial activity began in the late 1960s following discovery of oil in the Prudhoe Bay area in northern Alaska. And it's continuing today with new opportunities for leasing and oil exploration in the Arctic National Wildlife Refuge to the east. And these human developments carry on a decades-old debate over the global need for energy development versus the potential risks that that development has on wildlife systems, particularly caribou in the system. Caribou in the Arctic have been declining over the last few decades. So this graph is showing in red herds across the circumpolar north that have been in decline. In green, those that are increasing, and in the gray, ones that are stable. So this graph's a little bit outdated back from 2009. However, the global trends are remaining about the same. So across the circumpolar north, caribou herds are declining. And this is important because it threatens the food security of reliant communities, as caribou provide a very important subsistence resource for a lot of Arctic communities. And the traditional methods or conventional methods for understanding and monitoring trends in caribou are using radio telemetry, so either VHF or GPS collars that are fixed to individuals and tracking their movement over time, as well as aerial surveys that are used often to estimate population abundance. So these long-term landscape level monitoring strategies are essential in order for us to understand how these environmental and anthropogenic changes are impacting wildlife. But with new technologies and new tools, we need to continue to ask the question, how can we advance wildlife monitoring in the Arctic to continue to increase our capacity to monitor change? And one such technology that's been used around the world is known as camera traps, or also the remotely triggered cameras. And camera traps have been used in wildlife systems around the world, and they provide a lot of interesting insights into wildlife that once were not possible. And on the bottom here is a graph showing how many camera trap studies in the last few decades have occurred across the world. And you can see on the top here, top left, there's really relatively few in Alaska, and then generally over the Arctic, there's few examples of camera traps being used in those systems. So this is probably likely due to several reasons, but some particular challenges of using camera traps in the Arctic. First is that this is a really remote and difficult to access area. So that can make field work and logistics quite challenging. Also, this is a treeless environment, so there's not very many opportunities to use natural structures to mount these cameras. So that's something that needs to be overcome when you're conducting a camera trap study in the system. Next is that there's pretty harsh environmental conditions, particularly during the winter, where sub-freezing temperatures can reduce battery life of cameras. And then lastly, most terrestrial large mammals in this system are only seasonally in northern parts of the Arctic. So the wide ranges that these species occupy can make it challenging to sample them with a fixed sampling method like camera traps. So these are some of the things that we had to address and overcome in order to conduct our study in the Arctic. And just a brief overview of where this study took place. So like I mentioned, we were on the North Slope of Alaska. We started this project back in 2019, and we're just wrapping up our last field season now. So actually, Todd, who's on the call here, is currently in Dead Horse, Prudhoe Bay, collecting some of our field data for this last season. So we had a particular focus on caribou as our focal species for this study, just because of their social, cultural, and economic value. And in total, we had 40 camera traps that were deployed by helicopter in a systematic grid with sites separated by about 20 kilometers. And that's approximately the day range of caribou during this time. And we had two study regions. The first study region was in the Prudhoe Bay and surrounding area that's associated with relatively high anthropogenic development. And the other region was the Arctic National Wildlife Refuge 1002 area, which has relatively little anthropogenic activity. And at each of these camera sites, we had a camera trap that was recording motion detection images, as well as 5-minute interval time-lapse images from May through August during the summer. So at each site during each day, there was a minimum of 288 images recorded, assuming there was no technical difficulties or camera malfunctions. So this is just a general overview of our methods and our study area. But one of the first challenges we had to overcome that seemed simple, but actually took quite a bit of ingenuity was figuring out how in the world we were going to actually deploy these devices on the landscape. So our first season, we needed to figure out a way to develop some infrastructure in order to mount these cameras. And after a little bit of trial and error, what we ended up using was a gas-powered auger and a custom drill bit designed for drilling in frozen permafrost soils. And so we bored a hole into the ground and then installed a steel channel post into that hole. And that's what we used to mount our cameras at about the height of Caribou. And our cameras were housed in steel security enclosures, not necessarily for theft, but to protect it from the elements, as well as prevent any damage from wildlife. And so what we found was this method in terms of infrastructure and logistics worked really well. We only had a few camera failures, most related to bears coming around and rubbing up on the post and pushing them over. But generally, this setup worked pretty well. And so after we started collecting our first little bit of information, one of the very initial questions I had was, what was the spatial area from which we were actually drawing inference? And it was a little bit surprising once we started collecting information and looking at the images, just how far we could see caribou in the images. So the first few questions we wanted to address were, how far were these caribou from the camera? And a related question, how did they vary in size? And these two pieces of information can be used to answer a wide suite of questions. For example, distance estimates can be used for quantifying detection ranges, as well as estimating movement rates over consecutive images or in a distance sampling framework. And size estimates can be used to monitor physiological health, as well as distinguish between individuals or groups of animals. So we wanted to be able to answer these questions. And what we first did was look at the camera trapping literature to see what the current methods were to estimate these parameters. And the main methods, or generally the methods for estimating distance, relied on either a fixed reference object in the camera's field of view, as shown here in the middle, where they have stakes in the ground and they compare those to the position of animals and images, or calibrating the field of view of the camera using a fixed sampling grid of known dimensions, and then superimposing images of wildlife on that grid in order to determine distance. And the methods for estimating size are very similar, where they either use a fixed reference object or simulate a reference object in the image after the images have already been collected. And there's several reasons why these methods weren't going to work well in our system. First off, we were already collecting images, and our study was already well underway. And with the remote and difficult to access field sites, it was not really feasible for us to go back out to take these measurements in the field. Also, we wanted to minimize our human footprint on the landscape. So walking out across the tundra in this wide landscape in order to take reference marks at great distances was going to be challenging, as well as increase our human footprint on the landscape. So we looked at different fields to see how we could possibly integrate a different method for estimating these parameters. We came across a model in the field of photogrammetry known as the pinhole camera model. And this might be a little bit overwhelming with these equations and lines and stuff, but I'll try to break it down briefly. So essentially what the pinhole camera model is it's a conceptualized simplification of how cameras work. And essentially on the bottom right here, we have a camera that's taking an image of this deer in this case. And what the pinhole camera model does is it relates the three-dimensional scene being captured by the camera to the two-dimensional image being stored on the camera sensor. So on the bottom right here, SI is representing the size of the image or the size of the object on the image. DI is the focal length of the camera. DO is the distance to the actual object from the camera, and SO is the size of the object. So with the pinhole camera model, it allows us to relate these different parameters, and we wanted to figure out whether or not we could apply this in our system. The first thing we needed to do was figure out what the focal length of these cameras was. And unfortunately, most camera trap manufacturers don't report that information. So we needed a way to figure out how to derive this experimentally. So we came up with a calibration approach where we standardized for the other parameters in this model, which were the size of the object, which we standardized using this white piece of paper, and the distance, which we recorded. And then by isolating those parameters, we were able to estimate each camera's focal length expressed in pixels. We used software known as ImageJ to make those measurements. We also used two different camera trap models, each with two different camera settings. And the point of that was to make sure that this approach was going to work across camera trap models, across setups, to make sure that it was generalizable. And what we found was that derived focal lengths using this method were consistent across 3 replicates for each camera model and setting. So we were really confident that we could accurately derive the focal length of these cameras. And with that information, we were able to apply it. So the first step that we did was use this method to estimate distance and size in controlled settings to see how well it would work under ideal conditions. So we went out to a local archery range here and measured the distance and size of 5 different animal targets ranging from 5 to 25 meters from the target or from the camera. And we measured their nose to tail length and shoulder height. And on the bottom right here is my daughter helping collect some field data as a budding young scientist. And what we found was the total mean relative error of distance and size estimates using this approach was around 3%. Those are extremely accurate and extremely robust to different camera trap models, image settings, and measured dimensions. So we were excited to see how well this approach worked under ideal conditions, but what we wanted to do was try to think about how it would work under more realistic field conditions. So the next step was to do this in a more applied setting. So we went to the Large Animal Research Station at the University of Alaska Fairbanks and measured the size and distance of various caribou or reindeer at this research facility. And we measured 5 different morphological dimensions across 6 different individuals at distances ranging from 5 to 100 meters. And what we found was that mean relative error of distance and size estimates was around 10%, which is, again, really great. Much better than most people can guess, being able to tell distance or size from standing at that perspective. So we were really excited to see that this approach worked well. And we also found that these size and distance estimates were robust across individuals that we were measuring, camera models, and settings. So we were confident that it would work across camera models and settings and in different field conditions. So in summary, what we found with this study was that the key limitation of this approach is that you need to know either animal size to estimate distance or distance to estimate size. And in practice, what this means is you might be able to use established morphometrics on different species to estimate their distance, or you need to know reference distances to reference objects in the field of view in order to estimate size. And as long as those pieces of information are known, what we found was that this method addresses a lot of current limitations and challenges of other methods established in the camera trapping literature, or remaining pretty simple to conceptualize and implement. And then also estimates were robust across camera trap models. So this is a generalizable approach that we used in most conditions. And then finally, one big value of this approach is that it can be applied retrospectively after the images were already collected, which is what we ended up using it for. So that was a really positive attribute of this method. So with that down, we had started, at this point, we were probably maybe halfway through our first field season. and we just had collected our first big group of data, and we quickly realized that we were going to be generating a massive amount of data that we needed to figure out how to process. So the next question in chapter 2 that we addressed was, how can we effectively process these images? And by process, I mean being able to identify wildlife in them. So I'll give you a second, and I want you to look at this image and see how many caribou you can count. I'll give you a little bit of time. But initially, you probably saw these caribou close up. But what you may not have seen is these caribou on the horizon. So what we needed to see was, what were the trade-offs of using different approaches in order to process these images? And in the camera trapping literature, most people have turned to artificial intelligence and using machine learning models to automate these processing tasks. And there's a huge movement now into this automation of image processing, which has really helped address the big data challenges of camera trap studies, as the imbalance between data collection, the volume of data that you can collect very quickly, and the processing capacity to actually analyze that data is a big bottleneck for camera trap studies, and something we struggle with as well. The most basic data processing task for camera trap studies is generally object detection. So just determining whether or not there's an object in an image. And then the next step would be object classification. So assigning some class label to that object. So in this case, it would be caribou, or you might want to be able to tell the difference between a caribou and a moose. So whatever classes are relevant to your study. But generally, there's a trade-off between being really good at detection or being really good at classification. So there's a little bit of a balance there when developing these models. And so understanding how well these models work relative to human review is really important in order to inform how they could be used to try to complement or expedite reviewing of camera trap images. We focus on this topic, and after a while of looking at the literature and seeing different models, we ended up evaluating performance of the state-of-the-art computer vision model developed by Microsoft AI for Earth, known as Megadetector. And the reason why we focused on this in particular was because it offered a lot of promise for our system, particularly because it was a pre-trained model, meaning that it was already trained to detect animals using hundreds of thousands of images across the world. And it represented one of the only, quote unquote, out of the box computer vision models that's currently available for camera trapping literature, from the camera trapping literature, that can be applied pretty easily. And so we teamed up with the team at Microsoft, who ran our images, or a subset of our images, through this model. And our goal was to identify how well it could identify at least one animal in an image. So whether or not an image contained one animal or it didn't contain any. So we used a small subset of images, relatively small, about 6,000 images, with about an equal proportion of images that contained at least one animal and those that were empty. And most of these contained caribou, but there were a few other animal types that were in there. And this is an example of what the output is that we would see. So the blue bounding boxes are what the model's predicting an animal is in. And the yellow dots are ones that we manually identified. So what you can see is that it's identifying some of these animals, but not all of them. And so we wanted to more quantitatively address that. And so to manually label these images, we used a two-stage approach using the image review software called Time-Lapse 2. It's a pretty common image review software for camera trap studies. And in the first stage, we had at least 2 reviewers independently label wildlife in these images. And then in the second stage, any discrepancies in those initial labels were resolved to make a final determination of whether or not the image had an animal in it or not. And using those manually labeled images as the reference, we were able to determine whether or not the predictions from Megadetector were correct or incorrect. And then using that information, we identified the practical detection limits. So the minimum detection size and the maximum detection distance of both the camera motion detection sensor and these different image review methods using the distance estimation technique that I presented in chapter 1. So what we found was that megadetector worked exceptionally well on motion detection images. So for these images, it had an accuracy of about 95%, which is really great for camera trap studies that are using motion detection in close environments. But unfortunately, in our system, on our larger study, less than 1% of our total data volume was coming from motion detection images. So unfortunately, it wasn't going to work very well in our system. And the accuracy on time-lapse images dropped to 60%, which is just slightly above a random guess, which would be 50%. Unfortunately, it didn't look like this was going to be a very useful approach for us, but we wanted to understand more practical detection limits between these different methods. So using the minimum detection size, we applied the method, distance estimation method covered in chapter 1. So at the top here, we have a cropped caribou from the motion detection sensor. So that's the minimum size of the caribou that can be detected by the motion sensor of the camera. In the middle, we have the minimum size that can be detected by megadetector. And then on the bottom is the minimum size that we can detect using human vision. So using these minimum detection sizes, what we found was that the area sampled by the camera's motion detection sensor was approximately 60 times smaller than what megadetector could sample. And then moving from that, megadetector sampled an area about 132 times smaller than what human reviewers could see. So this just identifies some of the stark trade-offs between using these different methods to process images. So in summary, what we found was that motion detection underutilizes the area in the viewshed where either AI models or human reviewers can detect wildlife. This is a really important finding. And we found that evaluating and this camera model using a minimum detection size in conjunction with the distance estimation approach presented in chapter 1 provide a lot of practical information that can be used to help design camera trap studies. So being able to understand what the minimum detection size, maximum detection distance, and area sampled in the camera viewshed are. And then lastly, ultimately the decision of whether or not to use human review or these automated AI models will come down to how much effort you're willing to put into processing images and your accepted level of accuracy. So not one approach is objectively better than the other. It just depends on what types of questions and how much effort you're willing to apply. So moving on from this study, at this point, we had started to process about half of our first season of data. And based on the previous chapter, we were quite surprised about the stark difference in area sampled by the camera's motion detection sensor and time lapse. So we wanted to dive into that topic a little bit deeper and understand the actual impacts of different camera settings on the data generated in the system. So these were the topic that we focused on first. And most guidelines for camera trap studies focus on optimizing the camera's motion detection sensor to detect wildlife. So, but in open landscapes where motion detection may be less effective, there's a lack of information about how to program camera settings to optimize resources. So in chapter 2, as we identified, time-lapse has a potential value of increasing the area sampled in the camera's viewshed. But the challenge with time-lapse is being able to select a time-lapse interval that balances the trade-offs of detecting the animal with the resources spent on actually collecting and storing and processing the data. So this is one of the things that was lacking in the camera trapping literature and what we try to address. So the first thing that we did was evaluate the influence of camera trigger types, whether or not an image was triggered by motion detection or time lapse, as well as the time lapse interval length, so the predetermined time between images on caribou detections. And we used half of our data from our first season because that's what we had processed at the time. So this was data from the 20 sites in the Prudhoe Bay region. So we had a total of around 700,000 images In those were about 11,000 containing at least one caribou, accounting for about 500 caribou trap days. So a fairly large data set that we evaluated these different methods on. What we found was that trigger type 5-minute interval time lapse accounted for about 7/8 of the total number of images containing caribou, as well as detected about 94% of the days when caribou were present. So it accounted for most of our detections of caribou. However, it had a fairly low detection rate of only 1.4%. So very few images of the total data volume actually contained wildlife. Compared that to motion detection, this only accounted for about the remaining 8 of images containing caribou and only detected about 1/3 of the days when caribou were present. But motion detection had a much higher detection rate. So just some trade-offs there. And then moving on to assessing the influence of time-lapse interval length, what we did was simulated data sets with increasing interval lengths from 5 to 6 hours to see how those different interval lengths influence the data generated. And what we found was that to generate about as many images containing caribou as were detected by motion detection required a 30-minute time-lapse interval. And to identify about as many caribou trap days as were detected by motion detection required a time-lapse interval of about 4 hours. But the thing to point out here, and kind of the big takeaway here, is how big of an influence these shorter increases in time-lapse interval length can have. And so identifying how much data you need to address your study objectives, as well as how much resources you want to spend on collecting and processing the data is something that should be carefully considered. So in summary, for this chapter, what we found was that motion detection was more efficient with respect to data generation, as it had a higher proportion of images containing wildlife compared to those not, but at the expense of generating far fewer detections overall. And this relates to if you were to try to use time-lapse camera settings to generate the comparable data set, you would need to generate a higher volume of data. And this would increase the total amount of effort that you need to store and process the data. But there's several solutions to these costs. And the first being that you could process data using AI and to try to help automate this data processing task. The next is that you can use external battery packs or solar panels to extend the battery life of cameras, if that's a limitation of your study for whatever reason. And then lastly, you can use wireless or satellite camera traps to transfer data wirelessly to reduce the need for onboard data storage. However, these last two things, battery life and data storage, are probably not a significant limiting factor for most studies. But in cases where there's especially demanding applications, these two things can help. So just something to keep in mind. And then in terms of time-lapse interval length, we found that increasing the interval length had substantial impacts on the amount of information we were collecting. And so carefully considering exactly how much data or what type of data you need to address your study objectives is important. And this study provides an example for how to collect information in open landscapes. We just wanted to cover also the additional benefits of time-lapse, which include standardizing the sampling effort. So with time-lapse, you know exactly how many images you're going to be collecting, and they're triggered independent of animal presence. So it's a way to standardize sampling effort. Can also avoid any technical issues or differences in the performance of different camera motion detection sensors. And then lastly, it just makes this easier to plan for data storage, battery life, and processing time requirements of your study. So lots of benefits for time-lapse camera settings in open landscapes, but there's trade-offs for either setting. So now we're wrapping into the last chapter here. What we wanted to do was apply the insights that we gained from the first 3 chapters in order to answer something about caribou ecology using camera traps. And so what we tried to identify was distribution and habitat use during different seasons throughout the summer. And what we wanted to do was use this camera trap data in a way that we could make comparisons to conventional knowledge about caribou ecology. So for example, on the left here, we have the distribution and habitat use of the Central Arctic caribou herd based on radiotelemetry studies. And on the right here is the same things for the porcupine caribou herd based on radiotelemetry studies. So the idea was that we wanted to use camera trap data to try to create some comparable interpretations of caribou ecology to these. And just to briefly summarize what we're seeing here, on the top, we have calving for both the Central Arctic and the porcupine caribou herd. And we can see that it's kind of focused a little bit away from the coast on the southern end. And throughout the season, as the season progresses, from calving to post-calving and then mosquito harassment, caribou are shifting their distribution in response to those different seasons. So what we wanted to identify is how can camera traps be used to gain insight into these dynamics. And so just to cover where our study was again, we covered two regions. First was the Prudhoe Bay area on the west side here, represented in red, and this was associated with the Central Arctic caribou herd summer range. And then the next area was the Arctic National Wildlife Refuge to the east, represented in blue here, which is associated with the summer range of the porcupine caribou herd. And we assessed distribution and habitat use during 5 different biologically relevant seasons. And these seasons are dependent or are identified based on decades of studies on caribou ecology. And these included pre-calving, calving, post-calving, insect harassment, and late summer. And the distinctions between these seasons are somewhat variable between years, as well as between herds, and depending on which studies you look at. But there are general times at which caribou exhibit different behaviors. The exact distinctions of when the cutoff values of when those times are changes slightly. But for consistency, we just use these cutoff values for both herds during our study. And then we applied insights from our previous 3 chapters in order to develop a metric to describe distribution, which we call the relative use index. And so from chapter 1, what we did was we accounted for spatial variation in sampling by estimating the area sampled in each camera's viewshed, and used that to account for differences in detections based on variation in spatial sampling effort. And then from chapter 2, we still had data from the ANWR region that needed to be processed. And we elected to use a manual human review approach for that to maximize the area sampled, as well as generate the most accurate data set. And then from chapter 3, what we did was elected to only use time-lapse images. And the reason for that was to account for temporal variation in sampling effort. So by standardizing the number of images recorded at each site during each day, we would be able to eliminate this source of variation in our data. And then we compared site characteristics between areas where we observed and where we didn't observe caribou. And what we found was that our complete data set included about 1.2 million images. In those were about 17,000 containing at least one caribou, accounting for about 755 caribou trap days, but quite a large data set. And the next figure I'm going to show you might be a little bit overwhelming, but we're going to spend some time breaking it down. So this is a figure showing our relative use index. On the left in red here, we have the Prudhoe Bay area associated with the Central Arctic caribou herd, and in blue on the right, we have our National Wildlife Refuge area associated with the porcupine caribou herd. And then from top to bottom, we have the different biologically relevant seasons, starting with pre-calving all the way down to late summer. And then the shade of colors, darker shades represent that site was used more. Lighter shades represent the site was used less. Any site that has a star with a circle around it, like these up here, represent that no caribou were observed at these sites during the season. And then any site without a circle on it, like these here, represent sites where we had a technical failure. So these data were excluded from this season of data. So just breaking this down, what we found was the effect of environmental and spatial variables in habitat use. During pre-calving, what we found was that caribou were observed at sites that were warmer, with less snow cover further from the coast, and with lower density of roads. So you can see that here, it's reflected in our relative use index. So we can see that there's two kind of areas of high use down here to the southwest, and also the eastern portion of our sampling area. So these are further away from the coast generally, and further away from high densities of roads, which are concentrated a little bit closer to the coast. So these trends in these different environmental and spatial variables were consistent for the porcupine caribou herd, with the exception that there were no roads within 10 kilometers of our sites in ANWR. So that one's left out here. Moving on to the calving season, the effect of these environmental and spatial variables remain the same for both herds for the most part, but we see a slight northeastern shift in distribution based on the relative use index for the central Arctic caribou herd, as these concentrated areas start moving a little bit further east and to the north. And then for the porcupine caribou herd, we see a slight northwestern shift in use during the calving season. And then moving into the post-calving season, some of the effects of these environmental variables and spatial variables started to subside. So for the Prudhoe Bay area, the only variable that was significantly different between used and unused sites was that caribou were selecting for warmer sites. So there's now no longer an effect of distance to road road density or distance to coast. And then for the porcupine caribou herd, we found they were selecting for warmer sites as well as being further from the coast. But one thing to note about the post-calving season for the ANWR region is we had quite a few sites, let's see, like 6 or so, that were excluded based on camera failures. So one thing to note about that season. And then lastly, or not lastly, but the most dramatic change was during the insect harassment period. So we see an almost complete shift from, if you look at the pre-calving season, where caribou are concentrated more on the southern extent of our sampling ranges, that almost flips completely during the insect harassment season. So now caribou are concentrated along the coast, and a lot of these unused sites are on the southeastern portion of the central Arctic herd, and then a few in the central area of the porcupine caribou herd. And then we see a shift in the effect of these environmental and spatial variables, which is reflected here again by the relative use values, where caribou were selecting for cooler sites closer to the coast with a higher road density for the central Arctic herd, and then cooler sites for the porcupine caribou herd. And then finally, with late summer, for the central Arctic herd, they were still selecting for sites with higher road density as they're being concentrated up here to the northwest portion of our sampling area. But we see that they are starting to shift a little bit further south. So in the eastern section of this area, so in the previous season, these sites in the southeast were unoccupied or unused. So we see a slight shift, southern shift for the central Arctic herd. And that shift is more pronounced for the porcupine caribou herd. So we see that caribou were using sites further from the coast, and these sites along the coast are being unused. So this is supported. The porcupine caribou herd has a much longer migration between their summer and winter ranges, so they're known to spend less time on the summer range. So just one thing to note about that. Okay, so I know that was a lot, but some really interesting findings that we had based on camera trap data. And the interesting thing is that we found that camera trap data reflected pretty closely what we would expect based on conventional knowledge, based on radio telemetry and aerial survey data. But after looking at tens of thousands of images of caribou, this is actually the only image that we had of a radio collared caribou. So it's quite interesting and cool to see that we still came up with really similar insights, but with a completely different method. And just in summary, one example of how our results aligned with conventional data is on the top here. This is just one season. So we're just looking at the calving season here. And on the top, we have our relative use index to show distribution of use during the season for the two herds. And this is from our 2019 data. And then on the bottom here, we have two studies based on telemetry data showing calving concentration and distribution during this season. On the left here, this is for the Central Arctic herd, and this is calving distribution based on years from 2012 to 2017. And then on the right here, we have calving distribution from years 2012 to 2018. So there's a little bit of mismatch between years here, which could explain some of the differences, but generally what we see is that our relative use index aligned pretty closely with conventional knowledge based on telemetry data. So really exciting insights here, as well as a unique opportunity to learn from new perspectives with camera traps. For example, in terms of what we're actually sampling in terms of the population of caribou, camera traps are unbiased with respect to that sampling. So for example, most radio collars for caribou herds are on cows. And so particularly during seasons when cows can be behaving differently than the rest of the population, they may not be accurately representing what the entire herd is doing. And this is particularly relevant for calving, as well as later in the year during the fall, during the rut, when cows and bulls can be doing different things. Also, the inferences that we came up with based on this camera trap data is based on a larger sample of individual caribou. So for the Central Arctic herd, there's about 50 or so individuals that are collared, and that population is currently at about 30,000 individuals. And then for the porcupine caribou herd, there's about 100 individuals that are radio collared. And that population is currently at a peak of about 225,000 individuals. So the proportion of the herds that are actually radio collared is quite small. And our inferences are based on tens of thousands of images of caribou. So just an interesting insight there. And then also, one of the limitations or attributes of radio collaring is that you're only getting information on where the actual animal is, but it's not providing any insight on where it's not. So we're sampling using this fixed grid places that are also unused, so we can kind of start to get some insights on what conditions might be influencing avoidance of those areas. And then also, relative to radio collaring, camera traps are non-invasive, so they don't disturb the wildlife in any way. They're low cost and they're easy to implement. So another consideration when thinking about how to monitor these caribou. And then I just wanted to note that this is just our first approach at applying these data to try to answer something about caribou ecology. And there's a lot of opportunities to analyze this data using different approaches, as well as identifying how we can try to integrate these two information sources in order to gain new insights. So a lot of exciting opportunities here. Some future ways that this data can be used, while we can't identify unique individuals over time, since caribou have no unique individual markings, what we can identify and track is calves. So during the beginning of the season, obviously there's no calves as they're ending their spring migration, and then during calving, all of these calves appear, and so we can track their movement throughout the year. And so, for example, here, these are the icons of deer are where we first observed caribou at that site for each of these seasons. And then that's overlaid with our relative use index. And so what we can see is that where we are observing calves track pretty closely with our relative use index. So just another way to utilize this data and look at this data from a different perspective. And then also, there's a lot of opportunities to look at different things in terms of behavior. So we can look at different activity profiles during seasons. So these are total detections during each hour for each season. So just seeing how daily activity changes over time. You can also use the distance estimation technique that we developed in chapter 1 to estimate movement rates between consecutive images. And then also just looking at overall trends in these data over time to see whether we can help distinguish transitions from these different biologically relevant seasons and help identify differences in trends between herds. So there's other ways to look at this data and utilize the data. So in summary, what we did in chapter 1 was establish a method for estimating animal size or distance. And throughout the other chapters, we provided several examples of how that method can be applied to answer pretty cool new insights using camera trap data. In chapter 2, we identified some of the strengths and limitations of using automated tools to process camera trap images and provided some insights about the practical detection limits of these methods. In chapter 3, we evaluated how camera settings can substantially impact the amount of data that you're collecting and provided some guidelines for how to collect camera trap data in open landscapes. And then finally, in chapter 4, we applied knowledge that we gained from these first 3 chapters in order to estimate and use camera traps to estimate caribou distribution and habitat use, and demonstrated how these insights based on camera traps can help reinforce conventional knowledge of caribou behavior based on radiotelemetry and aerial surveys while providing opportunities to gain new insights. So collectively, we feel that this research builds a solid foundation to support the integration of camera trap monitoring for wildlife in the Arctic. And we look forward to seeing how that will change in the future. And then this is my last slide. And in closing, I'd just like to note that while my research focused specifically on caribou, by having a passive sampling method like camera traps, we collected information on tons of different species. So this is just a mosaic of all non-caribou or some of the non-caribou animals that we detected. And so there's opportunities to use this data in a lot of different ways and to answer a lot of different questions about how caribou are responding, or sorry, animals are responding in the Arctic. So just the last remarks is that regardless of which species you're focusing on, as the Arctic continues to experience rapid environmental change and changes in human activity, we just emphasize the need to think of creative ways to build capacity to monitor change in the system in order to inform sustainable management practices. And then what I think about when this, a thought that always crosses my mind when I think about the scale of the study is the saying, a picture is worth 1,000 words. And so at this point, we've generated about 7 million images. And so it's really daunting and exciting to think about what we can learn from that. So with that, I'd just like to thank you for being here. And special thanks to my funding people who funded this project, National Science Foundation, the UAF Graduate School, Department of Biology and Wildlife, and the Kelvin J. Lunsing Fellowship. Also the Institute of Arctic Biology for providing administrative support. And then my phenomenal committee, Todd Brinkman, Knut Keelan, Sean Crimmins, and Tim Fullman. I could not have been more pleased with their support throughout this process. It's awesome to have a committee that really supports and prioritizes your success. So I thank you guys very much for doing that for me. And with that, I'm done and hopefully be able to answer a few questions.